All right. So let's take a look at the exercises from section 5.4. Most of these first collection, or I guess about the first half of the exercises, are really just practice finding capital F functions. Should you ever see an integral without bounds, we're simply looking for the function capital F, well, a general form of the function capital F that would work using the fundamental theorem to compute the associated area. So the general form of all such capital Fs will include a plus C. It will be necessary to include a plus C on each of these exercises. But ultimately, like take this first exercise, we're just going to do what? 7x squared over 2 plus sine x plus C. So we're just finding the general expression for the antiderivative of the function of consideration within this integral. Were we to have bounds, a and b, on this integral, then you could take the capital F function that you would find for this exercise, plug in b, plug in a, and subtract, and you'd get the associated signed area between the graph of the function little f of x equals 7x plus cosine x and the horizontal axis. But in our case, since all we're doing is finding the general indefinite integral, indefinite meaning no bounds, definite integrals have bounds, we're just going to find the capital F function, as we said, 7x squared over 2 plus sine x plus c, and that's that. So let's see, moving down here, this is an example where, as I look at this, I wish I had a quotient rule for antiderivatives, but of course we don't have a quotient rule for antiderivatives. But we could take this x and divide it through each of the terms. I think we'll get something related to ln absolute x on the first term, and then all the other terms we'll just apply the power rule appropriately. I suppose the last term, x over x, comes out to be 1, so the antiderivative of that will just be x when that comes out in the wash. Don't forget your plus c, because every one of these indefinite integrals, we're not looking for the capital F function, because that's not really a thing. We're looking for the general form of a capital F function, which could include any plus c. Of course, we know when we would actually compute the area, the plus c term would cancel away when you do the capital F of b minus capital F of a. But for this exercise, or for any exercise of this form, the plus c is included. Okay, looking here, we got a sum. We just go term by term. For this last term, just remember there is an inverse trig function that relates to this. I believe tan to the -1 or tan inverse is our desired function. So that's something to look at. Here in this next example, I wish we had a product rule for antiderivatives, but we don't have a product rule for antiderivatives. So perhaps the best thing we can do is actually take that secant that's on the outside and distribute it through. If you do, you'll get a secant squared, well, 7 secant squared, I suppose, for that first term. And there is a function whose derivative is secant squared. I believe that's tangent. And then the second term will be a secant times a tangent. And again, there is a function whose derivative is secant tangent. So to find your capital F function, in this case, I think we'll end up with 7 tan t plus 6 secant t plus c. Again, the plus c for any indefinite integral, it's just par for the course. Okay, well, this is not too bad. That's just application of the power rule on each of those terms. Don't forget your signs. Be careful about your signs here in the middle, because you got this minus sign in between. And then what do you do down below? You take that general form of your indefinite integral, that capital F function that you produced up above, and then you plug in 6, you plug in 2 and subtract. Of course, the c's will go away, as one would expect. And then, yeah, the resulting value will be the signed area between this function's graph and the horizontal axis between 2 and 6, which is kind of mesmerizing to think that the integral can do such a thing in terms of computation, because I'm not even sure what this function looks like, and yet we can find the area. So that's pretty cool. Right. Okay, see here, this is an interesting example. If you were to try to do this, finding the capital F function of interest, it would be potentially quite sticky, because boy, we've got this this absolute value. So what my instinct here, let me just throw together a quick little snip so that I can talk through more precisely my instinct. my instinct here would be to first utilize the properties of our integral, which is to say, what just happened there? Which is to say, break this integral down between -1 and 2 of x dx minus 4 times the integral from -1 to 2 of absolute value x dx. I would do this because, well, this first bit is relatively straightforward to integrate, whereas this second bit, finding a capital F function for the absolute value function is not so obvious or apparent. However, if you think of the absolute value x function as simply a v-shaped function whose vertex is at the origin, like you know the absolute value function to be, then computing the associated area here is no more challenging than just finding areas of triangles. So I think I mentioned something about this in our last class, where if you ever get the absolute value function inside your integral when computing the area, finding the capital F function is really not the way to go, and you're sort of forced to use geometrical areas. So this is a classic example, a classic exercise, definitely one to keep in mind as a test writer. I would not hesitate to put a question with an absolute value inside an integral when computing area on a test, so that it forces you basically to use a geometric interpretation, because thinking geometrically, it turns out to be very, very fruitful in calculus, and a question like this almost practically forces you to think geometrically to process the information. So that's kind of cool. Okay, now we got to the second half of the exercises, and the second half of the exercises is all about the interpretation in terms of net change. And so the key factors to consider here are, I guess, one, not the bounds. The bounds will be important because those are giving you parameters on your variable, in this case t, likely a time variable, indeed, yes, because w prime measures pounds per year. Now, the second thing to keep in mind is the area associated, or excuse me, the units on the area associated with this region. And now if w prime is our function measured in pounds per year, and our time unit is measured in years, each rectangle of our Riemann sum would have a height of pounds per year and a width of year. And so if you take pounds per year times year, looking at this w prime times dt, right? Think of dt as a tiny width of the t-axis and the w prime as the height of our function w prime. We'd have pounds per year times year, that would be in pounds. So this should be giving us some pound-based information between year 7 and 12, which ultimately puts us on this line here. We've got a pound-based information between 7 and 12. Next example here, we've got gallons per minute as our R, and our dt would be some amount of time, so that would be some number of minutes. So gallons per minute for our R, some number of minutes for our time. Gallons per minute times minute would just be in gallons, and we've got gallons between 0 and 120. So one way that could be described is like during the first 2 hours, during the first 120 minutes, which I think may be terminology utilized, but nonetheless, we've got the idea there. Okay, nice. This next example is thinking in terms of velocity. Displacement is precisely what your excuse me, integral will compute. Because when we talk about displacement, if you go 100 miles east and 100 miles west and end up right back where you started, your displacement is 0. And so the integral computes this precisely because area above the horizontal axis is computed as positive motion, area beneath the horizontal axis computed as negative motion. And so the motion to the right and motion to the left would cancel out. And displacement then is just simply computing the integral of interest. So here we'd have the integral from 0 to 3 of 3t plus 5, whatever that pops out to be. You'd have to compute the antiderivative function, evaluate at 3, evaluate at 0, and subtract. Or alternatively, you could look at this geometrically, it's just a line. So since our velocity function is a line, the corresponding area regions which would be associated with the distance traveled would be just triangles, right? Whenever you would break it down. But even if you just use the fundamental theorem will give you the displacement, because displacement accounts for forward motion as positive distance and backwards motion as negative distance. Now, when it comes to total distance traveled, we want to think of all of our area region, both those above and below the horizontal axis, as positive, because total distance traveled would be like what the odometer of a car would read if you went a certain number of miles east and then maybe came back a certain number of miles west. Sure, displacement could be zero if you go 100 miles east and 100 miles west, but odometer would change by 200 miles if you went 100 miles east and 100 miles west. So in this case, in any case, whenever you're trying to compute total distance traveled, we've got to take our integral in bite-sized pieces. Here, looking at this function, let's see, that would intersect the horizontal axis at t equals 5/3. And so t equals 5/3 is a dividing line. Between 0 and 5/3, our velocity is either positive or negative. Between t equals 5/3 and 3, our velocity is either positive or negative, but our velocity is entirely positive or entirely negative on each of those two time intervals. So we need to break this down into two pieces, consider both of those integrals, and if either of those integrals spits back a negative value, that would be corresponding to a velocity which would be negative, a displacement which would be accounted for negatively, which here we have to force to be positive. So we take the integral between 0 and 5/3, and we take the integral between 5/3 and 3, and of our function 3t minus 5, and whichever of those two integrals comes out to be negative, we force it to be positive whenever we consider our total distance traveled. But well, that'll do the job there. Bacterial population between after 1 hour, let's see, we're per hour, so that's between 0 and 1, and we put our function in there, and then, well, we'd have to integrate this function. Remember, when you integrate an exponential function where the base is not e, if the base were e, the antiderivative of e to the t would just be e to the t. But when you take the derivative of 6 to the t, you'd get 6 to the t times ln 6, which means the antiderivative would be 6 to the t over ln 6. You'd be dividing by ln 6 in your response, and that's ultimately how you compute this guy. Right, well, that's just the fundamental theorem right here, right? If f prime is continuous, every continuous function has an antiderivative, and you can compute the area under the curve using the second fundamental theorem. Nothing fancy there. There is a subtlety in this question. Note the bounds here are between -4 and 1. And that presents a challenge because this function, 1 over x to the fourth, is not continuous on the interval from -4 to 1. So we can't simply apply the fundamental theorem. I bet if we applied the fundamental theorem, we'd get the result to the right. But equally true, the fundamental theorem cannot be applied here because the fundamental theorem demands that our function of interest be continuous. In this case, our function of interest is not continuous. So I have a strong suspicion this one turns out to be false, despite the fact that the fundamental theorem would give us -3 over 64. A well-written question, I must say. Definitely a trap question, to be sure. Let's see, if v of t is velocity, then this is the total distance traveled. I wish that was the total distance traveled, but remember, the traditional integral does not consider total distance traveled. Total distance traveled would count both east and west motion as positive, so you'd have to put absolute values on your v of t in that case, so that effectively you'd be considering speed instead of velocity. But since velocity can be positive and negative, if you integrated the velocity function, you would end up with displacement rather than distance traveled. Lastly here, if f has a discontinuity at 0, then blah, blah, blah doesn't exist. Is that necessarily true? I'm not exactly sure how our book defines an integral not existing, but it is conceivable for me to imagine that if the discontinuity was just a point of discontinuity, like maybe there was a jump because you had a piecewise function, you could very well integrate this thing, right? I mean, if you just had a piecewise function where between -1 and 0, a function did a certain thing, and then between 0 and 1, a function did something else, there could be a jump in the function, and yet integrating piecewise, you could compute the value. So I see no reason why this is not true. And if this turns out to be false, maybe we have a conversation there, but to have, because this is well, let's just double check. I believe the answer there is true, because I think I can put in the key here. Let me load up. False. I'm very surprised by this. So I don't love this question. If the discontinuity was as described, where you just had a piecewise function with a jump, this integral should exist. It should probably say then this integral cannot be computed via the second fundamental theorem. And if that's the case, that's certainly true, because you would have to break it into two integrals to do so. But yeah, this is not a well-written question. I guess based off the information we've got here, this should be false. And well, that's that. Hopefully this was helpful. And well, this gives you some discussion on the 5.4 exercises.